Okay, here we go. Yeah, welcome to the 3D seminar series. It's my pleasure to introduce Max Ovsjanikov. He's a professor at Ecole Polytechnique in France and works on 3D shape analysis with an emphasis on shape matching and correspondences. He has received a Eurographics Young Researcher Award in 2014 in recognition of his outstanding contributions to, wait a second. Sorry for that. I had YouTube open in another window. Okay, let's do this again. As I said, it's my pleasure to introduce Max Ovsjanikov, who's a professor at Ecole Polytechnique in France. He works on 3D shape analysis with emphasis on shape matching and correspondences. He has received the Eurographics Young Researcher Award in 2014 in recognition of his outstanding contributions to the theoretical foundations of non-rigid shape matching. In 2017, he received the prestigious ERC Starting Grant from the European Commission, and in 2018, he received a bronze medal from the French National Center for Scientific Research for research contributions in computer science. His main research topic include 3D shape comparison and deep learning on 3D data. And today he's going to talk about towards robust and efficient geometric deep learning for non-rigid shape processing. After the talk, we are going to have a panel discussion, and we are very happy to have three very distinguished panelists who are Emanuele Rodola, Michael Bronstein, and Peter Bonker. And with this, Mats, the floor is yours.
Okay, thank you very much, Torsten, and thank you for the invitation, and thanks to the organizers for this wonderful seminar. Also, thank you to the panelists. It's really a pleasure and an honor to see such great and familiar faces, and I hope we'll have a good discussion. So my talk today is about basically the title is Towards Robust and Efficient Geometric Deep Learning for Non-Rigid Shape Processing. And it's kind of a long title, but I wanted to emphasize two words. So is robust and non-rigid. And in my experience, those two words often don't go together. So today I'll basically try to say how we can make non-rigid shape processing a little bit more robust than usual. And this is joint work with many wonderful people. Most of them, especially my students, some of them are mentioned here, and I'll be mentioning the works as I go along. So, the general, as Torsten said, the general research directions in our group are especially kind of geared towards understanding and analyzing relations such as similarity and differences across geometric objects. So, point clouds, triangle meshes, even volumetric data. And the kind of goal for today, for the rest of my talk, I'll be primarily focusing on one problem, and this is the problem of shape correspondence or shape matching. And I think, if people have seen my work, I think that's probably the work that I've been doing most in the past 10 years or so. And the goal is actually very simple. So basically, I give you a pair of shapes, and your goal is to find correspondences, like point-to-point maps between these two shapes. And the shapes that we consider are typically non-rigid. And they can be, for example, like these human body scans, or they can be something more general, like we've recently worked with paleontologists who analyze jaws of prehistoric humans, or even with molecular surfaces. And ideally, the tools that we develop should not be limited to a particular class. We want them to be as generic as possible. So basically, if I kind of just specify this problem like today to a graduate student, so I give basically your goal is to solve the shape matching problem, right? So how would they kind of go about addressing it? And I think this is the general pipeline that you would kind of follow, right? So first we would start by gathering a lot of data. And then there's a kind of a standard thing to do, which is, convert your data into some input features. You create or, pick an architecture from like whatever exists. You design some training laws, and then you basically learn through back-propagation, okay? And so for the talk, I wanted to do something that I haven't done before, and kind of simulate this learning through back-propagation. And basically, I'll talk about these three components that go into kind of a typical pipeline. And I'll start by talking about the training laws. And then, I'll talk a little bit about architecture design, and finally, I'll talk about, features and feature design, what kind of features we can get for 3D data. And as an inspiration for my talk today, I wanted to use this image, which is a drawing by Herbert Edelbrunner. And if some of you maybe have seen, Herbert is known for drawing these beautiful, very characteristic images. And this one I particularly like, and it's actually a quote from a Austrian rock band, and it's I guess a free translation from German, and it says, "Noise is always and everywhere." And apparently in German it sounds just as awkward as it does in English, but I think it makes actually a very, very strong point, which is basically, whenever you're dealing with data, there's always going to be noise, and you have to do something to deal with it. So that's my kind of main inspiration. So basically, starting from talking about data sets. So if you kind of just start doing non-rigid shape analysis or shape correspondence, you'll probably look online and you find these kind of existing data sets. So the most common ones are Faust or their extensions like dFaust and Serial. There's a little bit older ones like Scape and Tosca that Michael and his colleagues created. And the nice thing about these data sets is that, first of all, they're clean manifold triangle meshes, and you have ground truth maps. So that's perfect, for learning. But on the other hand, you have to be very careful because, first of all, these data sets are synthetic. And what that means is that, these are not scans, individual scans, but they're typically templates fitted to a particular shape. So basically all the shapes in the collection are in one-to-one correspondence. And indeed, even the vertex IDs are typically ordered. So basically, vertex 10 in shape 1 corresponds to vertex 10 in shape 100. And this means that you have to be very, very careful when you're doing learning, because it's very easy to overfit. And also the typical scale of data sets that we have is quite limited. So, there are not so many data sets with, hundreds or thousands of non-rigid shapes that have ground truth correspondences. And this is a real challenge, and this will come back again and again in the rest of my talk, basically how to deal with this. Now, for me, the story of this kind of non-Euclidean learning starts with basically the works of Michael Bronstein and his colleagues. So there's a wonderful survey that was published in 2017 on geometric deep learning, and there's kind of a more recent updated version by other authors, also kind of on more recent techniques in geometric deep learning. And the problem is this, right? So, we all know how to do learning on, for example, images. You have these powerful convolutional neural networks. And when you're dealing with non-Euclidean data, such as, non-rigid surfaces, you have to do something else, right? So basically this geometric deep learning is this field of applying learning techniques to non-rigid shapes and doing it on a surface. And there are many different approaches. So just like as a kind of an umbrella approach, although this is maybe not characteristic of all of them, but one thing that you can do if you have a surface is that you can't have a global parameterization like you have on an image, but you can have a local parameterization. So basically, if you have a point X, around this point, in the neighborhood of the point, you can parameterize it through a kind of radial coordinate system. And if you do that, then basically you can have a signal F, and then you can design or learn a kernel, and then you can multiply this kernel basically with respect to this signal, and then you get some number. And this gives you a kind of a learnable local convolution operator. And the nice thing is that everything is intrinsic, so this is pose invariant. And so this was originally introduced in the same as GCNN work in 2015, and since then it's been extended a lot to many different settings. So this is by no means like the only approach you can do, but they often have this kind of flavor. So without going into details about the architecture, one thing that I wanted to emphasize is basically the choice of laws. So when you're learning, and actually, shape matching was one of the inspirations for this original work. So when you're learning for shape correspondence, how do you formulate the right laws in your learning pipeline? So one standard approach to do is basically to treat correspondence as a labeling problem. So if you have a query shape X and some template reference shape Y, then basically for every capital shape capital X and a point little x on the shape, you can say, what is the corresponding point on this template, right? And you can treat it as a label, right? So you can think of it as a kind of a semantic segmentation problem. And the, a typical loss that you can do is a kind of a logistic regression loss, where it basically says that, okay, I have some ground truth correspondence for this point x, and this is basically this delta, so the indicator function at this ground truth correspondence y star, and then I have the predicted correspondence or the predicted label by the network, and so the standard approach is basically do this kind of cross entropy loss, and so you can impose this loss on the parameters of the network, and then you can learn the optimal parameters, right? So this is nice because we know that logistic regression or cross entropy works well, and so we kind of leverage existing tools. But on the other hand, it has some limitations. So first of all, this loss is independent of the geometry in the following sense. So suppose that for this point x, the ground truth prediction is y star, but actually I predict some point nearby. So whether I predict a point nearby or a point very, very far away, the loss is going to be the same, right? So this is kind of an issue because sometimes we're willing to make small errors. Also, the other problem is that this requires a template. And so what that means is, for example, if I have two shapes that are like in a different class, in order to map between those two shapes, I first have to map to the template and then map back. And so you have to do this kind of map inversion, which is not trivial. And then, of course, this requires ground truth dense correspondence. Right? So this is one approach that you can do. And actually, designing good loss for shape matching is surprisingly not a trivial problem. So this is why I wanted to spend some time talking about it. So just to give an example of a kind of approach that you maybe can see, you basically using this cross entropy loss and like an advanced version of a JCNN. So this is a paper from from last year from CVPR. It's called ASCNN. And basically, this is exactly what they do. They have an advanced JCNN and they do this cross entropy loss. And if you look at basically the errors that they get, so here, these are the kinds of plots that you see in shape matching, where you have on the x-axis the geodesic error, on the y-axis you have the percentage of correspondences below a certain threshold, and so basically you see that you're at like 100% correspondences are basically close to zero error. So you even have to zoom in to like distinguish 99.5 from 98.5 here, right? And so, if you look at these kind of results, you would think, okay, this correspondence problem is solved, right? I mean, we're basically getting zero error on this standard benchmark. But now, this is kind of where this noise issue comes in. If you do a little bit more analysis, so you basically take a look at these shapes and then train for correspondence with the original shapes, but then let's say you just remesh them a little bit, right? So you modify the mesh triangulation. And all of a sudden, an error that was close to zero basically jumps to something that's like, this is showing the distribution of the error, and this is 10% of the shape diameter. And all of a sudden, basically, this correspondence error jumps to something extremely high. So what this is saying is that perhaps we didn't actually learn something about the geometry of the shape, but perhaps we instead learned something about the mesh connectivity, or maybe we even overfitted to just the vertex IDs because they're ordered in a particular data set. And this is true not only for this ASCNN, but it's true for many existing techniques in this field, which is, they can show good results on a particular data set where you have a clean manifold mesh, but as soon as you start remeshing, you can, get very significant errors. And so basically for the rest of the talk, I wanted to discuss, what are some of the things that we can do in order to alleviate these problems, right? So the first issue is that this cross-entropy loss does not capture the shape geometry, as I mentioned. The second issue is that local patch operations, like this parameterization that I mentioned earlier, is often slow and not very robust. And the last thing is that, we require ground truth. So, kind of how do we overcome these problems? And one approach, or at least one beginning of an approach, is by, so like how do we kind of compute globally coherent correspondences efficiently? And so the one, beginning of an approach is going to the Fourier domain and using basically spectral techniques. And this is something that, I've been very excited about. And so, I wanted to mention it now, how this is useful to solve these problems. So in order to introduce it, I have to take a little step back and basically talk about signal processing on surfaces. So many of you, I think, are familiar with this already, but just a quick recap. So basically, if you have a surface, then there's a very natural generalization of Fourier analysis, and this is given by basically the eigenfunctions of the Laplacian operator or Laplacian matrix. So for every surface, there's a Laplacian matrix, and you can compute the eigenfunctions of this Laplacian matrix, and they basically give a generalization of Fourier analysis, like sines and cosines to more general domains like graphs and surfaces. And they have nice links, I mean, very similar properties as Fourier series. So first of all, there's a natural notion of frequency, and basically the eigenfunctions are ordered by eigenvalues, right? So they go from lower frequency to higher frequency. And then another approach that, or another property that's extremely useful is that basically given any function, you can, on a surface, you can represent it as a linear combination of these basis functions with some scalar coefficients. So this is very similar to expressing a function, for example, on a periodic domain as a linear combination of Fourier series. Right, so there are many other things you can say about this Laplacian eigenfunctions, but for the rest of my talk, for my talk, this is the most important property. So, given this, like, how does this help us in the shape correspondence problem? So there is a concept that we introduced with some colleagues like 9 years ago, and it's called functional maps. And the idea is the following. So if I have now, if I have a shape and a function on that shape, I can represent it as a linear combination of these basis functions. Now, if I have another shape that is in correspondence to this one, and I have basically the corresponding function on this shape, then I can represent it as a linear combination with respect to the basis functions of this shape. And what you can show is that there's always a matrix C such that if I take the coefficients of the function f and stack them as a vector, then the coefficients of this function g that's also stacked as a vector must be represented as some matrix C times this vector A, right? And this matrix C is what we call the functional map. And I mean, there's actually a closed form expression for, so basically if I have a pair of shapes and I can encode a point-to-point map between these pair of shapes in the binary matrix pi, such that, for every row of this binary matrix, I just store the index of the, or I put a 1 in the ID of the corresponding point, then the functional map is just a projection of this binary matrix into the corresponding basis functions, right? And the advantage of this representation is that, first of all, this functional map matrix is much smaller than the original point-to-point matrix, and there are many natural constraints that you can impose on this functional map C, and they're easy to express. So basically, instead of dealing with matrices of size, number of vertices on the source times by number of vertices on the target, you can typically deal with matrices that are 50 by 50 or 100 by 100 at most. And so, using this representation, there's a basic kind of pipeline for solving shape matching problem, and it consists of the following steps. So first, we compute k, some small number of Laplacian eigenfunctions on the two shapes. We store them as matrices of these, as columns of matrices phi m and phi n. And then we compute the optimal k by k functional map by solving the following problem. So first, we have a term that basically says, we want this functional map C to align some coefficients and or coefficients of some descriptors. And second, we have another term that basically says that this functional map C should commute with the Laplacian operators of the two shapes. And this term basically is a kind of a prior that says, we expect the geodesic distances of the two of the map of the shapes to be preserved under the map. Meaning that if I have a pair of points on the source and I measure the geodesic distance before, then if I map those points, the geodesic distance should be small. So this is kind of the expression of that constraint in the spectral domain. And finally, we convert this computed functional map matrix into a point-to-point map by mapping delta functions. So we wrote a kind of a course, SIGGRAPH course with kind of colleagues, and both Michael and Emma are contributors to this course. So this is just a very, very simplest version of the functional map pipeline. And there are many, many more advanced versions that are described in this course. So if you're interested, I can recommend taking a look at that. One thing I wanted to say briefly is that this last step of converting a functional map to a point-to-point map, it actually took us a very long time to basically find the right formalism. And so there's a paper that came out this year's CVPR where we basically describe, kind of the theoretically correct way of converting functional maps to point-to-point maps. And we also make a link to optimal transport in spectral methods. So this is just a reference. I won't go into detail, but now finally we actually know properly how to do this. So that's the small aside. Okay. So the thing is, if you are careful enough and you compute, your descriptors and all the parameters carefully, then you can compute good correspondences. But the question is, what happens if your descriptors are bad, right? So if in this pipeline, if you have poor descriptors that are not in alignment, so for example, these are short descriptors on a pair of shapes, then if you compute functional map and do texture transfer, then you get these, you can get significant error, like there's a lot of distortion in the mapped texture. So, what can you do, right? And one the first approach that I know of that incorporated functional maps into a deep learning pipeline was introduced in this paper FMNet from 2017 by Litani and colleagues. And what they propose is the following. So suppose that I start with some descriptors, and instead of computing the functional map directly from those descriptors, I first pass them through some standard MLP layers. So basically these are learned layers. And then after I pass them through these learnable layers, then I can project them onto the basis of the two shapes, compute the functional map here. And this is an important thing, that basically this FM layer is not trainable. So it directly solves the linear system inside the network. And then this functional map is converted to a soft correspondence, and then there's some loss imposed. So the important thing is that, first of all, this functional map layer is given by a linear system of equations. And it doesn't have any parameters, but you can back-propagate through a linear system in, for example, TensorFlow, right? And the loss they use is not a cross-entropy loss, but it's basically a loss that's imposed on the soft correspondence. And the soft correspondence, first, you take a functional map that's small, you convert it to a large matrix, like an assignment matrix that has the size of the number of points in the source by the number of points in the target. And then for every prediction between pair of points x and y, we basically penalize it by the distance between the ground truth map that you should have from the point x to this point y. So this is the geodesic distance. Okay, and the key advantage is that this loss basically evaluates the entire map. So instead of evaluating point by point, it actually kind of has a global consistency on the map, and it as a result kind of gave the state-of-the-art results in 2017. Now, the first kind of step for us in this direction of like trying to improve this pipeline was in 2019, where we said, okay, let's take this idea, but let's see if we can make it fully unsupervised, right? And this gave rise to this paper that appeared in ICCD in 2019, that like an architecture that we called SurfMNet. And the idea was very, very simple. So we took the exact same architecture as FMNet. So we start with some descriptors, then we pass them through some learnable layers. Now, instead of computing a single functional map from shape 1 to shape 2, we compute basically functional maps in both directions, right? And then we impose some loss on these computed functional maps. And this loss is purely unsupervised. Now, I should mention that there was a parallel paper that was done independently at the same time by Halimi and colleagues that had very similar goals, but they used slightly different techniques. So I'll focus on the losses that we use. So in this unsupervised SurfM network, we had a set of losses, and this is something that I think is kind of, in general, interesting because these losses that came from our kind of axiomatic analysis of functional maps, but they turn out to be useful in learning as well. So the first thing is that if I have a pair of maps from shape 1 to shape 2 and another map from shape 2 to shape 1, we want them to be basically inverses of each other. So the first loss is that when I compose these two maps, I should get back identity. The second loss is that we expect these functional map matrices typically to be area preserving. So that means that if I have a patch on the surface, the area of that patch should be the same before and after I do the mapping, and that corresponds to having orthonormal matrices. Also, as I mentioned, there's this commutativity with the Laplacian, which is kind of near isometry, so the preservation of geodesic distances. And then there's a kind of a more technical term, which is, that functional map should be close to a point-to-point point. So I won't talk about this. And the nice thing is that all of these penalties are in the reduced basis. We never have to convert a functional map to a large, n by m matrix. And so these matrices are like 30 by 30 or 50 by 50. And so this is extremely fast to train. So this is 50 times faster on average to train than FMNet. Now, one thing that we did is basically try to evaluate how well we can do, but in order to basically not overfit to the triangle mesh, we also looked at this remeshed versions of the Faust dataset. And this is this remeshed version, something that we released as part of a SIGGRAPH paper in 2018. And the nice thing is that, the meshes are not too different, but at least they're sufficiently different that you cannot overfit to the vertex IDs, right? And basically in this 2019 work, we compared to existing techniques at the time, and it was, achieving kind of state-of-the-art results on these remeshed data sets. And these plots that I'm showing here, they're much more modest than the plots that you might see in some of the papers that work on just this original Faust data set. But I think they kind of are a little bit closer to reality that you see on actual shapes, right? So the other interesting thing is that this work, even though it's unsupervised, actually achieved better results than some of the supervised methods. And to me, it's also saying that even if you have the ground truth, it's kind of not enough. It also is extremely important how you impose this losses, and with unsupervised losses, you can sometimes get just as good results. So here are some texture transfer results using this approach. And basically, I won't say that, these are better results than supervised methods because, it depends how you compare things and like exactly how much data you have. But it's at least on par at the time. So this is, now 2 years ago, and so it's a bit obsolete. So there are much better results since then. But still, this was comparable to the supervised techniques at the time, which I thought was kind of interesting. Now, so on the one hand, this was promising and got us excited to work in this area. But on the other hand, it also had some limitations. So the first limitation is that we used these pre-computed short descriptors. These are axiomatically defined descriptors as input to the network. So the question that we next pose is, can we use the raw geometry, like the XYZ coordinates, to learn features from? And the second question is, how well do different methods generalize across different data sets? So remember I said that if you use the template, it's very difficult to train one data set and test on another. So we try to see how well existing methods actually could do. And this led to a paper that appeared in CVPR last year. It's called Deep Geometric Functional Maps. And basically, the idea was that first, let's learn the features directly from point clouds. And secondly, let's kind of, so there's another contribution that I'll mention in just a second. So the main goal is to extract descriptor functions from the raw geometry. And in this work, we used basically a training loss in the spectral domain. And this training loss was just very simple, taking a functional map and comparing it to the ground truth functional map. And what is the ground truth functional map? Is just the ground truth point-to-point map projected onto the spectral basis. And we used general kind of Siamese network architecture as in the SurfMNet work before. But instead of using the short descriptors, we used the coordinate functions, and we used this KP-conv feature extractor. So the nice thing about this loss is, first of all, it penalizes the whole map, like the map as a whole. It also does not require a template, and it does not require geodesic distance matrices. So this makes it much faster to train. And another thing that we introduced is basically, remember that in the previous like FMNet and the SurfMNet, we only computed the functional map by solving one part of this functional map optimization problem by just inverting a linear system. But we also show how to basically incorporate the Laplacian commutativity as a regularizer inside the network. So this was done by Nicola Donati, the student.
Max.
Yes?
I have a question. Sorry, maybe you mentioned it, but so in this case, X and Y, you actually have the mesh connectivity. but you only use the vertices to compute the descriptors, but you have the connectivity. Okay.
Exactly. Yes.
So this is not a point cloud Laplacian.
No. So we use the connectivity of, so we use the mesh Laplacian to compute the eigenfunctions, but then we use the point clouds to compute as inputs to the feature network.
Max, maybe a follow-up to this question. So how do you ensure that you get, for example, invariance under Euclidean transformations, right? So you probably want not to be sensitive to the embedding of your mesh.
Yes. So here, I mean, we use basically. So this is actually a very important question. So first, we can use data augmentation. That's actually what we did for ensuring invariance. But it's actually important because here we use the supervised loss, and ideally we would like to use the unsupervised loss that we had before. But this basically, if you have a unsupervised loss that we had in the spectral domain, it's not sensitive to surface orientation. So what that means is that we can get, for example, the mixture between left and right? And so the loss is not aware of the orientation. The loss is fully, intrinsic, but the shapes, of course, are, they have an embedding. So in this work, we actually use the supervised loss to combat this fact. So basically, to make sure that we get something that's aware of the shape embedding. And to get invariance, we just use data augmentation. So I'll talk a little bit how this was extended later. Okay. So yeah, so this is this additional regularizer in the network, and that seems to help to regularize learning significantly. And so these are the kinds of results that we got. And the nice thing is that because we basically use the spectral loss, it seems to allow us to learn with much less data, right? So compared to, for example, 3D coded, which was a powerful method at the time that required a lot of training data, we could basically, even with 100 shapes, we could learn something that was both robust because it used the point cloud as input to the feature network, and also accurate because it was based on this supervised learning setting. Right? So this was our kind of stepping stone last year, and since then, so maybe just as a small thing, so we also evaluated on this remeshed Shrek dataset. So this is a much more kind of challenging dataset, and basically, again, I mean, these plots are much more modest than what we see in training on testing on fast shapes, for example. But I think they're a little bit more realistic. So we can achieve some reasonable error, even though it's still far from perfect. One thing I want to mention is that a lot of these examples are shown on human shapes, and there are some other techniques that work explicitly by using the human shape template. So fitting, for example, the simple parametric model. But as I mentioned, we try to develop things that are more generic. So this is not using the fact that it's humans in any way. Right? Okay, so this was kind of the stepping stone for us. But there are two still major issues. The first one is that we are using an extrinsic feature extractor. So this is something that both Michael and Marietta alluded to. And this is this KP-Comb feature extractor. So this is just based on point clouds. But we have surfaces, right? So somehow it seems, kind of natural to try to learn directly on the surface. So this is something that we want to kind of improve. And so the general question is, how do you enable robust and efficient intrinsic learning on surfaces? So robust, I really want to emphasize, because basically, a lot of the architectures can be efficient and can be accurate, but often are not robust to remeshing. So this is a work that, so for the rest of the talk, I'll mostly be talking about works that are either non-published or very recent. And so this is a work that I particularly got excited about, and it's still not published, but it's on arXiv, and basically it's at first we called it diffusion is all you need, and kind of became a little bit more down to earth. It's called DiffusionNet, discretization agnostic learning on surfaces. And so this is work with Nick Sharp, Keen Crane, and Suhaib Ataiki. And the idea is basically create a surface-based learning technique, but it's that is ideally as robust as possible. So as I mentioned, the typical pipeline is that we have some geodesic convolution, and we have a pooling hierarchy. And both of these operations are quite difficult to discretize in surfaces, and they can be sources of non-robustness. I mean, it's kind of amazing that they can be done in the first place. But in our experience, they can be also sources of some non-robustness. So the idea is to just use diffusion, right? So basically replace both of these operations with simple diffusion. Okay, so this DiffusionNet architecture that we proposed has three components. So it has pointwise MLPs, it has learned diffusion layer, and it has gradient features. So pointwise MLPs is something very simple, like even PointNet, that I won't discuss in too much detail. But the two other blocks are learned diffusion and gradient features. These are kind of the key things that make this architecture be effective. So how does it work? So first we use a learned diffusion layer. So basically, what is diffusion? I mean, diffusion is something extremely simple and very kind of general. So suppose that I have some distribution, let's say, of heat at time t, and it's governed by this partial differential equations, like the simplest probably partial differential equation, that the evolution of heat in time is given by the Laplacian times the heat at current time. And this is like a simple linear PDE that is defined on surfaces, with like discrete differential geometry. It's extremely well studied. It's super, robust. There are many different implementations on both, meshes and point clouds and even more general domains. And so, kind of intuitively, if you have a point source, let's say on this 3D shape of a hand, and you let it diffuse, it becomes, a little bit like it kind of explores this neighborhood a bit more, and then eventually you have this constant temperature over the entire surface, right? And so the first idea in this work is the following. So let's have a diffusion block that basically takes some feature and diffuses it, but let's make the diffusion time a learned parameter, right? And that parameter can be dependent on other things, but basically, we have some like across different features, feature blocks, we can have their own diffusion time. It's not specified. So we have a variable, basically spatial support by choosing this diffusion time, and it can range from purely local to totally global. And this is something that allows us to basically not use any pooling hierarchy because the network can decide if it needs to have a local support or global support by choosing the right diffusion time. And this is optimized during training. So we have this parameter t for every layer. And there's a nice lemma that actually was shown by Nick. So Nick Sharp is the first author in this work, which is that diffusion plus pointwise MLPs can represent all radially symmetric convolutions. So basically, it's equivalent. Either you have radially symmetric convolutions or you have diffusion plus pointwise MLPs. It's basically equivalent. So this is the first building block. The second building block is that typically we don't want to limit ourselves to only radially symmetric filter. So radially symmetric filter basically is something that doesn't depend on the direction, right? And that's typically not enough for learning something that's more powerful. So we have an extra layer, or extra building block, which is the basically a gradient feature. And what it does is the following. So we start with some function on the surface. We first compute the gradient of that function at a point, so that gives us this vector. And for every feature function, we have its own gradient. And now we basically take these gradients and then we take inner products between these gradients, where each of the gradients is basically scaled by some scalar value a. And actually, there's a little trick, which is that you can, if you represent this matrix in complex form, you can represent both scaling and rotation. Okay, so when we have outward pointing normals, we also have we can scale a gradient and also rotate it before taking this inner product, and that makes the expressive power a bit more. So this basically makes us aware of the outward orientation. And this is very important, is basically this is invariant to the choice of the tangent plane. So there's no local parameterization. Okay. So now the last thing is, how do you evaluate diffusion? And so there are many different ways of doing, computing diffusion on the surface or in a graph. And what we do is basically just, so in this work, we just represent diffusion in the spectral domain. So we have some signal x. We first project it onto the spectral features. We then apply the learned diffusion. So here this is a per eigenvalue multiplication, and then we multiply it again, right? So this is one important thing. So this, by the way, here should be T0. So because we're applying the same time across all eigenvalues. So this is very important to mention here that this is not spectral learning. So we don't have any filters that are dependent on a particular frequency. So this is just one way to do to simulate diffusion. So in the paper we also compare it to another way, which is using a backward Euler. And what's nice is that this approach basically allows you to just do dense matrix multiplication, and this learnable parameters are just these values t. You can also do sparse matrix inversion and then make the learnable parameter t again, but this is a little bit slower, right? But these are just two different ways of simulating diffusion.
Max.
Yeah.
So you do the diffusion the spectral way, so to speak, and you do this in a reduced basis, or?
Yes. So this is, yeah.
Okay, so it could be, well, so you lose some properties that you would get with the Euler step method,
yes,
right?
Absolutely, yeah, definitely. So there is a limitation here, and actually this is kind of interesting. I mean, I'll show some results, but even though we do this diffusion in the reduced basis, and I think it's using like 128 basis functions, which seems not too many, but because we also have these MLPs and gradient blocks, in the end, it turns out like to be able to capture very local details as well. So that's
okay. Mm-hmm.
So I have another question. So here, do I understand correctly that this is limited to homogeneous isotropic diffusion, right? So basically, your Laplacian is independent on the features or on the data that lives on the manifold. It depends only on the structure of the manifold.
Exactly. So this is an important point. So here we basically only have radially symmetric. So this is homogeneous diffusion, and the only place where we have something that depends on the features is here in this gradient features, right? And this, so we basically simulate the directionality not through the diffusion, but through choice of this gradient features. So here we have some learned multiplication.
But this is completely separate from the data, right? So it doesn't depend on the data. So it depends on some local orientation that you can prescribe at every point of the manifold. So you can scale your gradient, right? If you think of the Laplacian as divergence of the gradient, so you can rotate and scale the gradient based on some local vector field, right? So that's what you do. Is it correct?
So maybe let me show for the overall pipeline, right? It might be a little bit more clear. So the first step is, we have some input, right, to the network. Then we have this projection of this input feature or this input into the spectral basis. So this is just the coefficient. Then we have this learned diffusion, and this is a homogeneous diffusion, right? So it's not. So you see this TJ is basically a fixed time per block, but it doesn't depend on the eigenvalue or it doesn't depend on the data. Then we have basically these two things that happen. So first, you compute the gradient of this diffused feature, and this gradient of the diffused feature, so this is now a vector in the tangent space, and we have basically these learned scalings and rotations of the gradients, okay, of these tangent vectors. And so we basically take these learned features that are diffused, compute their gradients, scale them and rotate them, take the inner product between the scaled and rotated gradients, and then convert them back to a pointwise feature, okay? And so now we have these basically features that are coming either from the inner products of gradients or from the diffused original features, and then they're basically stacked and apply some MLP on top.
But the diffusion is not feature dependent, right? So if the analogy in image processing would be the Perron-Einmalig diffusion, right, where basically that this allows to diffuse across pixels with different brightness.
I think it's maybe a little bit subtle because so you're right that it's not dependent on the data, but it's dependent on the feature channel. So we have a different diffusion time for different channels.
Okay.
And that's like, it allows you to basically have different, specifications.
I see.
Yeah.
You are not mixing channels, right? So each channel is separate.
Yes, but it's mixed afterwards. So this is a single block, and then we stack these blocks on top of each other. So that, I mean, eventually they, I guess, get combined.
Thanks.
Max,
Yeah.
sorry if I'm insisting, but so I just now realized that you're taking the gradient of the learned diffusion.
Yes.
So since you're doing it with a reduced spectral basis, I can imagine the gradient will have a lot of singularities, and those you wouldn't have if you take the Euler step. Because you have no guarantee that you have like an increasing function from the source.
So wait, so here this is in the reduced basis.
Mm-hmm. Mm-hmm.
But so then we convert back to the spatial basis. This is the
yes.
Mm-hmm. And then you can take the gradient, right?
Right.
And so in the reduced basis, if you have a small number of eigenfunctions, I think you should have fewer singularities, right? Or you have fewer. These are smooth functions, right? So we compute gradients of smooth functions.
But I imagine that once you project back, well, once you reconstruct in the spatial domain, you would get oscillations. Now, if you have oscillations and you compute the gradient,
mm-hmm.
then you would have singularities when well, at the creases and valleys of the oscillations.
Yes, that's. I'm not sure singularities are. So like for example, the gradient of a heat kernel signature, for example, right?
Mm-hmm.
Is very smooth, except for like a small number of singularities. I think you can basically, they're small gradients, but I don't know if they're really singular.
Okay. But you didn't have any issues in this sense.
No,
okay.
It's actually extremely robust. So that's kind of.
Okay.
Yeah. Okay, so this is this is the overall pipeline, and this is like a single diffusion net block, and then you can basically put many blocks on top of each other, right? So yeah, basically, we then applied this idea on many different tasks, and we did, for example, this RNA molecule segmentation. We also did functional correspondence, and like there are many. I mean, there are many results in this archive paper, but basically for each of these, there's we achieved state-of-the-art results. So let me just maybe kind of show a couple of these results. So first of all, we use this DiffusionNet as a architecture for training geometric deep functional maps. So using the same supervised laws that I showed before. And basically, if you take this, so here we are using the connectivity, right? So we are using the surface, and with the same feature. So here in the beginning, for example, we take the HKS as an input feature to the network, and so this is so now because the feature is rotation invariant, and also the diffusion blocks are themselves rotation invariant. So this entire thing is fully rotation invariant, but it's trained with a supervised loss, and so this achieves basically better results than any other method that we tested against in this setting. And we try different things like training on one data set, or training on another data set, or training on one and then testing on another, or in both directions. And in all settings, we basically get better results. So another thing that's important is that this is extremely fast, because the kind of the bulk of the work is done in the reduced basis. So if you have a mesh with, let's say, 150,000 vertices, it's still basically it doesn't really, it scales extremely well with respect to the size of the mesh, right? And it only requires like a quick recomputation of the Laplacian basis. And the other thing that's important is we also try basically using full size meshes or point clouds, and we don't require downsampling, right? So there's some intrinsic learning methods, like for example, mesh CNN, that's very difficult to make work on dense meshes, but here it's even with limited memory, it's fairly practical. So another thing I wanted to show is basically predicting vertex IDs with DiffusionNet. So here is this, the same problem that I mentioned earlier, where we train a network to predict the ID of the vertex on the template. So this is using this cross-entropy loss, right? And what's I think interesting is that, so this is, if you train for this prediction on the original data set, and so we don't overfit. And I think this is probably where, so there's some residual error. It's not exactly zero. And I think probably this residual error is very, very small, but it's there. And this is probably coming from the fact that we are using this reduced basis, but it actually helps to gain some robustness. So now, if we remesh the shapes, we are, it's still extremely graceful. So you have basically very small error regardless of the mesh connectivity. And what's interesting is here we're just using this prediction of the vertex ID. So, like we're not overfitting to the vertex order because the meshes are completely different. And here is also an interesting result that we actually trained on the original shapes, but then we applied this trained network on the sampled point cloud, and we use a point cloud Laplacian to compute the diffusion. And even there, the error is like significantly lower than what you get with other approaches. So this is, I think, like, because we have these only two very simple building blocks, which is diffusion and gradients, it kind of helps to gain robustness to changes in triangulation. So yeah, this is these results of diffusion. Now, okay, so maybe in the rest of my talk, which I have like 10-15 minutes, I want to talk about the last bit, which is how do we extract input features? And this is like some of the more ongoing work, and I think also I find it kind of exciting. So the first, kind of motivation is that, like, I think in 3D domain we have some a kind of a gap between what exists in other standard computer vision. So if you have non-rigid shapes, we have like axiomatic geometric features like heat kernel signature, for example, or shot, but they often have limitations. So first of all, they might have theoretical guarantees, but they're either not robust, like shot, to changes in triangulation, or have some limited expressive power. We also have learning-based features that may be, like, for example, from this KP-Conv, or from even DiffusionNet, starting from X, Y, Z. They have great expressiveness, but they might require some training data. But even the bigger problem is that they often don't generalize well, right, across different shapes or classes. And this is kind of in contrast to what exists in computer vision, right? So, like, it's very rare you see people using SIFT, for example, nowadays. So we have these generic feature extractors that are trained for image classification, and they allow transfer learning, right? And so somehow we still don't have that in non-rigid shape analysis, which I find interesting and a bit unfortunate. So the two questions that are kind of related, actually. So first is, can we train generic features that could be useful for non-rigid shape analysis? And as an aside, I wanted to mention, like, can we remove descriptors altogether from functional map computations? Okay, so I'll start, just say a few words about the second topic first, and I'll finish my presentation by discussing this first question. So, we have a couple of recent works that try to basically, instead of using some descriptors, try to compute correspondences directly without any descriptors at all. And for this, you need to do something which is explore the map landscape. So here's a pair of shapes, and each point in this diagram is basically a correspondence, a point-to-point map, and the y, like how height is related to basically the geodesic distortion of that map. So you see this very complicated landscape, and there's some local minima, like, for example, corresponding to symmetries, and there's some like global minima that's corresponding to some like kind of ground truth correspondences often. But exploring this entire landscape is very difficult. And actually, this is where descriptors come in often, because they allow you to like start at least in some neighborhood, and then you can do some, let's say, local investigation. So to address this, we had this work that appeared in last year's SIGGRAPH, and the idea is, we call map tree, and the idea is to basically organize maps in a spectral domain, and organize them along frequency. So basically, we have this kind of graph or a tree that at the root has like only 1 by 1 map, and then we have these leaves that basically correspond to different expansions, like larger and larger functional maps, right? And in this paper, we show how you can progressively explore the space of maps through this expansion, and how you can basically keep only sufficiently good in different maps. I won't talk about this in detail, but the whole thing is that we never rely on any kind of descriptors or features, only on this correspondences as a whole. And so, just as a few results, so basically these are, this allows you to compute not only a single correspondence, but multiple correspondences, and often there are multiple possible solutions that correspond to high quality maps that correspond to maybe symmetries, or you have like different man-made shapes that have different symmetries, or even like a complex is not with multiple intrinsic symmetries. And we can explore this through this map tree approach. And another thing that I wanted to mention briefly is that we also try to remove basically features or descriptors from the functional map pipeline. And the like little kind of as an aside, so remember that I showed this original functional map energy, right? That shows basically, you compute a correspondence C that aligns descriptors and commutes with Laplacian. But if you remove the descriptors, then C equals to 0 is a global optimal of this energy, right? So if you just remove descriptors, in principle, you cannot compute a functional map directly. So in this paper that's about to come out with SGP, we basically show that you can replace an unconstrained optimization problem with a constrained optimization problem that says, let's look for a correspondence for a functional map C that has to arise from some point-to-point map, but we don't know which one, and that commutes with Laplacian. And so what we show is that for a wide range of energies, including this Laplacian commutativity, the point-to-point map can be recovered basically in closed form if this functional map is fixed. So we have this alternating discrete optimization problem. And so here's just some like funny results where you have some initial shape, you have an initial like random point-to-point map that absolutely has no like structure at all. And then if you compute this unconstrained optimization, then you get something with like a functional map that's essentially like very close to 0. And with the discrete optimization, you can, even in the case of like, some non-isometry, you can compute decent point-to-point maps. Okay, so this is basically one approach of how to remove descriptors from functional map communication. Okay, and so just to finish, I wanted to mention one work that is ongoing and it's not published, but I think is interesting just in terms of the direction, and somehow I feel it's also a little bit underexplored. So basically, the inspiration for us was this work by Z and Orlitani and colleagues, and it's called point contrast. And basically, in this work, what they show is that in many tasks for 3D shape analysis, you can pre-train powerful features by using a contrastive loss. And so this is kind of standard now in 2D computer vision, using like contrastive loss pre-training. And then you can use it for a variety of downstream tasks like shape classification, segmentation, and detection, right? And so one question that we asked is, can we apply the same idea for non-rigid shape analysis? Yeah. And like surprisingly, I mean, to me, it's kind of interesting that like so far there isn't really a link between non-rigid shape analysis and this kind of feature pre-training. And so this is ongoing joint work with a postdoc that is in my group, Lei Li, Sohaib Atiki, who's a PhD student, and Hongbo Fu. And our basically goal is to do a generic feature pre-training. And so what we do is we first have so we use this data set called 3D Match, which has a whole bunch of indoor scenes. And so we basically compute we have an unsupervised point registration task. So what I'd like to do is basically have these scenes, compute some descriptors on the points of these scenes, and then align these scenes like rigidly, right? And we have an unsupervised registration loss for rigid alignment. And then there's also like a small contrastive loss, which actually is somewhat less important. But the registration loss is actually exactly the same as what we have in this unsupervised surfing network, where we basically first, have some putative correspondences. We solve a linear system for the rotation and translation parameters, and then we impose constraints, like we want the rotation to be orthogonal, we want the determinant to be 1, we want basically the rotation in the two directions to cancel each other out, etc. So this is our unsupervised registration loss. Okay, and so this gives us some features of these on these indoor scans. And now what we'd like to do is basically use these features for different downstream tasks. And just like maybe as an illustration, so here's a feature that was learned for this rigid correspondence task, and we computed non-rigid correspondences just by using nearest neighbors of these features. And here I find it kind of interesting, first of all, because these features are fully learnable. They're based on differentiable voxelization, so they're extremely robust, right? They're and they don't care about sampling, for example. They're also rotation invariant and have local context. And what is even more amazing is that they're never trained on non-rigid shapes. So these features have never seen non-rigid shapes at all. I mean, they've only seen indoor scans. And yet somehow they managed to find these reasonable correspondences. And so here are some other results of like basically just correspondences in nearest neighbor in the feature space. So even though like there's some noise, right? So they're not perfect by any means, but they're still like picking up some very strong signal. And to me, it's exciting because it's saying something that's like, there's really some geometry that these features are learning, and it's really kind of robust, right? So so we basically took these features and then tried to apply different learning strategies on top of them. And so for example, for this RNA molecule segmentation, so we took these pre-trained features, we call them Vader features for voxelized alignment based descriptors. And if you like remarkably, because these features have never been, kind of like they have nothing to do with molecules, but because they encode very powerful signals about local geometry, they can be used for a variety of tasks, like for example, molecule segmentation or non-rigid human part segmentation. So we, if you, for example, train DiffusionNet using XYZ coordinates, you get like, 90.6%, and you get like close to 92% just by training on top of these pre-trained features. And we also, so this is my last slide, we also applied this to unsupervised learning for shape correspondence. And basically by using these pre-trained features, because they are rotation invariant and are aware of local context, we can basically learn, with using an unsupervised loss, right? Previously, for this deep functional maps, we needed a supervised loss. But now, because we have this kind of built-in rotation invariance, we can apply an unsupervised loss. We have unaligned data sets, so they're, they're not like rigidly aligned in any way. We have this different, DiffusionNet with different input features. And these are, by the way, this point contrast features that I mentioned earlier. So they actually work somewhat well for some classes, but they don't generalize very well across classes. So you can get a pretty significant error of this point contrast feature. And this is also results with no post-processing, so you can get even better results with post-processing. Yeah, so I mean, to me, it's exciting. I mean, it's kind of still early stages, but it's exciting because it's making this link between rigid world and like scene analysis and non-rigid shape analysis, which I think is kind of fertile area. Right, so that's kind of all I wanted to mention for today. So basically, I talked about three main things. So first of all, using spectral techniques for imposing losses that treat the correspondence as a whole, both with and without supervision. And this DiffusionNet as an architecture for robust and efficient surface-based learning. Finally, about these generic pre-trained features from unsupervised scene alignment to non-rigid analysis. And maybe just kind of as an invitation for the discussion, and also mention some challenges at the end. So I didn't talk at all about, for example, partial non-rigid matching. I know, like, for example, Emanuele's worked a lot on this, but I think there's a lot of work to be done still, and we are still far from getting something that's both robust and accurate for partial non-rigid. So basically matching not entire shapes, but only parts of shapes. Also, non-rigid correspondences in cluttered and noisy point clouds, I think is something we're not very good at yet. And another thing that I think is exciting, and I know that, for example, Michael's working on this, is correspondences and other domains like graphs or high-dimensional data or ordered data, like maybe videos or something like that. And something as more general, we definitely need more and better data for the kind of more realistic and more challenging tasks. So yeah, and I want to thank all my wonderful collaborators and my funding agencies. So thank you very much.
Max, thank you very much for the very interesting, great talk. Yeah, with that, we go to the panel discussion. I'm not sure if you have anything out of the back of your head that you would like to start discussing.
I can start if there are nobody volunteers. So I liked very much the DiffusionNet paper. I should say that I was not aware of this work, so we recently had a paper in the domain of graph neural networks. It will appear in ICML, where we took very similar approach as well. So we call it grand graph neural diffusion PDs. And the idea, well, the implementation is very different, but the idea is also this kind of approach that diffusion is all you need. Basically, what we show that a very broad class of graph neural networks can be represented as diffusion processes on graphs. So in our case, it's nonlinear diffusion, that is non-homogeneous. So we actually solve numerically the diffusion PDE, not in the spectral domain. It exactly mimics the attention function that is used in graph neural networks, in many types of graph neural networks. Mm-hmm. With the advantage, of course, that you don't need to do fixed step discretization in time, like is done basically corresponding to a layer of graph neural network, but we can use adaptive multi-step schemes like Runge-Kutta, or we can use also implicit or semi-implicit schemes like that invert the diffusion operator. So this corresponds to what is done sometimes in graph neural networks with multi-hop filters. So I like very much this analogy between diffusion processes and well, call it convolution type architectures or attention type architectures. So I wanted to hear your take on this. Well, I understand that now you're plugging DiffusionNet everywhere. So yeah. Do you think that it can substitute explicit convolution filters on manifolds that existed before?
So I've seen your work, and I think it is really, I mean, it was, I only came across it like recently, a couple of weeks ago. And yeah, it's definitely, there's a very nice link. And I mean, it's kind of amazing that there's this like confluence of ideas of, diffusion as a powerful mechanism. I think, basically the fact that like we use this diffusion, I think that's something that's very, very powerful. And I think that's, it also really contributes to the robustness from what I've seen. I think there's definitely some like maybe other, even more kind of like generic or more extendable things that we can do that could be improved. Like, for example, we use these gradient features, and I think the gradient features are powerful, but I'm not 100% sure they're really always the right approach to injecting some directionality. So maybe using some like learned anisotropy, for example, for the diffusion could be. I think that would be like an alternative. To me, I guess it potentially could be a little bit more expensive. So there's probably some trade-off to be done there. And also, I think there's some things that could be interesting about like even applying maybe attention on top of the different features that we have, because we have a feature per feature diffusion, right? But you can also try to think about like combining different features together and then having some kind of joint information that kind of boosts different features on top of each other. And I think that's probably a promising direction.
It has been done actually in image processing. So, well, my PhD advisor on Kimmel, so they had in '95 a paper that is called Beltrami flow. So basically, joint space where you represent the positional coordinates of pixels in an image in this case, but you can think of nodes on the measure or on the graph, and the feature coordinates, which are, let's say, colors of the pixel, and they evolve them together. So basically, you can think of a color image as a two-dimensional manifold in R5, right? Mm-hmm. With some non-Euclidean metric that in that case was of course fixed and crafted, but with modern deep learning pipelines can be made learnable. So this is actually a follow-up paper on the grant diffusion that where we look at positional encoding of the graph.
Yeah, definitely. I completely agree. There's also, I think, something maybe interesting to be done that we haven't done at all is that like once you learn the diffusion parameters, they're kind of fixed, right? And this is, I think something that is both nice, but also is a limitation, right? Because the diffusion parameter can be learned, but it could be learned through like a subnetwork that maybe depends on the data itself, right? So there's, I think, a lot of possibility even after doing after enabling learnable diffusion. Because right now we just have this per channel diffusion, and then you learn it, and it's basically done. It doesn't depend on the data at all, right? But I think that it doesn't have to be that.
Well, you could also replace the Laplacian with a parameterized operator and then learn the parameters of the operator. So you have a wider family of diffusion processes.
Yes, definitely. Yeah. I would say that I would maybe be a little bit careful about that, because then I also think that there's sometimes, you can make things like through, for example, local, I don't know, like for example, this ASCNN, that's kind of what they do a little bit. I mean, they also do this like parameterization of the diffusion through like anisotropic diffusion, and they kind of learn the parameters of that. But I feel there's a trade-off also, like the more, expressive you make things, then sometimes you can also make it a little bit more prone to overfitting. So that's kind of bias variance trade-off. So I guess you have to be careful.
I also liked very much the unsupervised part, and this is something that we've been recently looking into as well in a different domain that is also very geometric kind of problems, but they're probably a little bit underexplored in computer graphics and geometry processing. And this is protein biology. So where you design proteins. Well, with Emma, we had a paper that actually appeared on the cover of Nature Methods, where we applied geometric deep learning architectures to understand the binding of proteins. It's essentially supervised problem where we know that two proteins bind together, so we have complementary parts. It's slightly more complex than the pure geometry, so there are also chemical features, but overall it's very clear, tangible geometric problem. So the main issue there is that you have a lot of proteins for which you know the structure. It is very difficult to get co-crystallized protein pairs where you know that they bind together and they sit together, so you know what corresponds to what. So therefore, there is big interest potentially in unsupervised techniques. So I've seen a few works on contrastive learning. Do you think that there are analogies to what is done, for example, in NLP techniques, where you have these masking approaches, where you have, for example, a sequence of tokens, and you mask out one of them, and you try to predict it from the context?
Oh, that's interesting. Yeah, I don't know. It's definitely, it's definitely. Overall, I think this unsupervised pre-training is super underexplored in like graphics or geometry processing. I mean, especially for non-rigid shapes, there's, almost nothing, right? So I'm kind of just excited to get anything at all. But yeah, I mean, the space of possibilities is really vast, right? So. But I guess my understanding is that this contrastive loss, like, is, you can do, for example, masking, but maybe it can then introduce some parameters, and it's like you have to be a little bit careful exactly how you do the masking, for instance. So I think that Alyosha Efros had this like whole thing about what should be contrastive and contrastive learning, right? Yeah, I mean. So in this work, like what we did, there's actually no synthetic examples, and I kind of like that. Like basically, we have pairs of scenes, right? We don't create synthetic examples by, for example, taking a scene and removing parts or anything like that, right? So here we have just pairs of scenes, and we try to align them, and we know there should be alignable. I guess that's the only supervision that we have, right? But I guess if I had to kind of cast a vote, maybe the somewhat uninformed vote, is that I feel there's a lot of potential for like if we don't create synthetic examples, because as soon as you start creating synthetic examples, you can also introduce some bias about what exactly you're, how you're training, and that can be a little bit dangerous. But I think by avoiding like creating synthetic examples, you can, and being a little bit more creative about like what do you do with the data, I think you can get also more robustness.
So the alignment of scenes, so you do introduce some, inductive bias, if you wish, so some assumption that that we have scenes that can be geometrically aligned, right?
Rigid. Yeah, that's so that's this 3D match data set. I mean, that's like the premise, I think, of this data set, right? But other than that, that's, I guess,
but if I take the problem of proteins there, it is not straightforward because you don't have matching alignable surfaces. You actually have complementary surfaces that are complementary both geometrically and chemically. So roughly speaking, well, right? They need to have opposite charges, otherwise they will be repelling each other. So what would be the solution for that kind of situations?
Yeah, that's a good question. I guess I don't know that data well enough to say anything meaningful, but I feel, there is at least, we're basing everything on alignment, right? And like similarity, but maybe in some cases, having some kind of a dissimilarity, like basically, I guess in the case of like opposite charges, you want things to be close. If they're like the more dissimilar their charges, the closer they should be, something like that. I think that's something that probably in that kind of setting would work. But honestly, you would know much better than me. So. But just as a small thing, I think, there is at least like in this work that, again, it's ongoing, but I think it's kind of, interesting just to discuss. Like the fact that we can, for example, like we've never seen proteins, or we've never even seen like humans, right? And yet we can extract some information about the geometry. I think that's saying something about like the fact that geometry is learnable more broadly, right? Like there's some basic geometric principles that could be part.
It's not surprising because this is local geometry, right? And we can argue that locally, whether it's a human finger or a part of a protein molecular surface, or I don't know, a corner of a table in a room, they all look the same, right? So these are kind of geometric primitives, and it's not very surprising that it works for deformable shapes because deformable shapes locally are rigid, right?
Yeah, I guess it's not a miracle, but yeah.
So let me ask one simple question. You didn't like the use of synthetic data, but that seems to be the core ingredient that makes it work in the image domain. So wouldn't it be more straightforward to first start with the synthetic data to mimic what has been done in the image domain, and then see what you can get by eliminating it? Or
well, I guess, yeah, I think of course you're right, but maybe I'm still like a couple of years behind in the image domain. Like I'm thinking, about, for example, retraining on ImageNet, like supervised, right, for classification. And that's, in my mind, that's very like, okay, that's something you can do. Of course, if you want to do unsupervised, you can do contrastive learning and so on. But I guess I started by saying like, okay, if we have even some supervision, like it's okay as long as we can learn some powerful generic geometric features. And I think even for that, we're not super close yet. But I think you're totally right also that, yeah, mimicking the, like, I guess that's what this point contrast, that's a little bit what they try to do, is basically take the I think there was a CNRS data set and create synthetic examples out of that. Yeah, I think that was kind of what their motivation was.
Max, so you also mentioned, maybe in one of the earlier works, where you were using data augmentation, right? And we had this brief discussion how you make your descriptors or your deep learning pipeline in general invariant or equivariant. So this is actually quite a big trend now in machine learning in general, is how to get rid of data augmentation if you know a priori what is the symmetry group that acts on your data. And what is the right way of doing it for let's say 3D geometric data, right, or for deformable shapes?
Yeah, so this is, I mean, this is a great question. And I mean, I guess, so I didn't talk about this at all, but we also had a couple of papers in this direction, especially with my previous student, Adrien Rudenard, who worked on this, how to basically create invariant and equivariant networks, both rigid and non-rigid under different transformations. So I think, I mean, I would say that right now I don't think there's like a clear universal solution, especially for 3D data. And I mean, if you look at the best, like for example, for classification or even for correspondence, there's usually a gap between, for example, like rotation invariant or even equivariant features or a result that you get from just doing data augmentation. So I don't think we're there yet. Maybe I can just comment for the context of shape correspondence, because this is something I looked at a lot. So, in the shape correspondence world, we have this big problem of symmetries, right? So I think just like factoring out symmetries is often enough to get good results, right? So you don't need full rotation invariant, right? If you just know, for example, where the left is and where the right is, typically that's enough to get, to get good accurate correspondence, because everything else is already, you can do from local geometry. But this global orientation is the only, like, I mean, is the only thing that really, like, you cannot see from the local geometry. And there, I think we have a few different solutions. I mean, basically, like, even just doing like left-right classification somehow. So that's like with a separate approach. That's one option. Like doing the symmetry exploration as another option. Another option that actually we're working on now is basically only restricting to orientation preserving correspondences. And that's something that you can do. And basically this is, I mean, it's not trivial, but it's something you can do even in the functional domain. And so basically I would say this, especially for non-rigid shape processing, I think the more, like, rather than imposing invariance to like overall like global transformations, in my experience, it's kind of more productive to enforce invariance to the intrinsic transformations, like the intrinsic symmetries, for example.
Max, I have a question on the robustness part of your talk. Mm-hmm. So that part I enjoyed a lot. So I think that's a very important problem we have to address as a community. Now I see, mm-hmm, on the one hand, we are striving to build pipelines that are robust to the data. So to different representations, to the noise that we might encounter due to sensor noise, for instance, and so on and so forth. On the other hand, we have a good part of the community, from the 3D computer vision and geometry processing community, that are concentrating on models like taking implicit representations to produce, I don't know, more faithful generative models or higher quality representations in the end. Now, of course, if you switch to an implicit representation, then you sidestep many of the issues that you mentioned. And I'm kind of surprised that we are not bridging the gap between these two things. So what's your thoughts on this?
Yeah, no, I think that's an excellent point. And yeah, I think this is, something that I think, I mean, first of all, I believe there are multiple people already working on this. And this is, something that we've discussed a little bit is, basically doing, so right now, I think the implicit representations, as you mentioned, they're mostly used for generative models, but they're not so much used for analysis tasks, right, or processing.
Right.
And so the natural question is, how do you use them for, let's say, analysis, right? And so, like, even on CPR, there's a paper, for example, doing some, surface correspondence using, implicit representations, even though in a very partial sense. So that does exist. I guess at the moment, one of the limitations is like having precise enough, like, even I think, as far as I know, the best implicit representations, they're still lacking some local detail that could be important. So there's a little bit of a bottleneck there, right? But it's also true that probably the amount of error that we're making in some of the tasks, like matching point clouds, is probably not worse than what you get in reconstruction. Mm-hmm. So yeah, I definitely agree. I mean, I guess there are many like building blocks that need to be there, and I guess basically overall, I would just say that you're right. I think the kind of the time, it's a good time now to try to do this. Yeah, because it is definitely true that it's very robust, and you can get like quite good reconstructions. One thing I actually wanted to mention is, maybe I'm going to plug this one thing in this domain, is that we have a paper this year, CPR, about also like generative models for like shape optimization, and there's this kind of a limitation of some of the implicit surface representations, is that they can naturally produce like multiple connected components, for example, or shapes that are like not stable under gravity and so on. So with some additional tools, you can like promote, for example, shapes like implicit surfaces that represent only a single connected component using basically topology tools, and you can learn this in an end-to-end way. So this is something that we worked on that I think could be useful. I mean, this is just like pure advertisement, so could be useful.
Of course, what I think is that the implicit representation stays useful as long as you don't need to materialize the surface at some point.
Yes. Yes.
So you want to do all the processing and the manipulation in an implicit way. You want to stay there, right?
Yes, yes, that's true. Yeah, yeah. So you want to delay it until the end.
Mm-hmm. Yeah.
But the reconstruction itself is certainly a source of error, or potential source of error. You need to somehow make it more accurate.
Mm-hmm.
But it's definitely a very good point.
Max, so maybe this is open-ended broad question. So where do you see, well, the field and yourself working in maybe the next 5 or 10 years? Because, well, we know each other for since probably 2007. So it's interesting to see how basically the field has transformed and how we drifted also from across topics. But there is somehow a common thread to more or less everything that you do, right? So it's well, obviously differential geometry, right? So it's also spectral methods, and now the deep learning is the new shiny tool, and you try to combine, well, and many others as well in this field try to combine it with geometry. So where do you see it leading us in this decade?
Yeah, I mean, this is a very good question. I don't know if I can answer it faithfully, but one thing that I can say just for myself is that, despite the fact that there's, deep learning is a new shiny tool, I think some of the, insights that we had before are still applicable, right? And at least for myself, I'm still excited to work on, basic tasks like, modeling, even in an axiomatic way, modeling, surfaces, doing like more robust analysis and like careful theoretical analysis, for example, of like this CPR paper this year I mentioned, is there's no deep learning. There's more about like some basic things about how to convert functional maps to point-to-point maps. So I think that at least that will keep us occupied for some time, and I don't think that's, I hope it won't go away. Basically, there's still a lot of value for understanding relations between objects in an axiomatic way. So that's one direction that I definitely will want to continue. And one thing that I hope to also do is, I don't know, from my perspective, it's interesting to analyze not only similarity, but also differences. So like detect, where and how objects are different. I think that's something that, we have some tools for, but it's still, I would say, kind of basic. Like, for example, we have some discussions with surgeons, and that's really something they're interested in, right? Like if you have somebody who's a patient who's healing, is he healing properly, or does someone have an anomaly, and if there's an anomaly, like what exactly is it? And that requires both finding relations but also differences. And I think modeling differences, something I think Leo, for example, also advocates quite a bit. I think creating better tools for that, I think that's definitely important. But also from the maybe learning perspective, if I had to guess, I guess I would say that like going across different representations and like also having tools that really understand something about the geometry I think that's it's a bit subtle because you have maybe a sense that all of the different architectures understand some part of the geometry, but it's not always obvious, and basically my kind of general question is, how do you make sure that we have something that's both robust and has geometric sensitivity to geometry, even in higher dimensional settings? So that's, I don't know, that's at least something I find interesting.
So maybe this is a bit of an ironic comment. So probably 10 years ago, if you're pitching spectral methods to computer vision experts, let's say, they would say, oh, but these require very clean data, right? So they don't really work in the real world. And now, from your works, what you see in the field in general, it was pretty much possible to make these methods work on noisy data, incomplete data. And what role did deep learning play in the success, and what is just the natural progress of geometry and more robust numerical techniques, in your opinion?
I think, well, I would say I would probably say that you would be able to answer that question better than me, but maybe one thing that I think we can do better as a community also is to advertise our tools and make the tools more generically applicable. Like, not only say, okay, we're working on surfaces and that's all we care about, right? But I think, also you and Emma and Peter also have done great works in making things applicable on, let's say with some modifications, for example, on graphs, right? Or on point clouds, or, on other representations. And I think that's something that we can definitely do. And I think deep learning provides that kind of link sometimes, right? Like if you have a building block, if you can modify it or adapt it so that it's applicable to a different domain, I think that makes it very, very powerful. And I think that's, kind of we're getting better and better at doing that. And I think in large part thanks to your contributions.
So let me ask that in a more direct manner, because you look at the functional maps pipeline and then you say, oh, can I replace the features? But why not replace everything with deep learning? Why not replace the functional maps part? What's the vision? Is deep learning going to replace the functional maps and then the spectral methods and then the differential geometry, so that basically people throw in the raw data and they don't need to know anything and out comes something in 10 years?
Well, first of all, I hope not, because I think there's, okay, so maybe from my perspective, I don't think that will happen for two reasons. The first reason is, if there's enough data, right? I think that's a big if. And my sense is that it's unlikely we'll ever be, there where basically there is so much data that, you don't need any kind of inductive bias, right? I think in the image domain that maybe is more likely, right? And we've seen that much more, but in the kind of geometric domain, it seems a little bit less likely because, the scale is just not there, right? So we definitely, I think, need, well, at least in my kind of visible future, I think we'll need some inductive bias, right? And also, I think even when you do have a lot of data, the amount of supervision that we have is typically quite low, right? So you might have many, I don't know, thousands of shapes, but they're very rarely annotated. And when they are annotated, it's a major effort, but still, it's still maybe tens of thousands at most, or hundreds of thousands. And so I think that's where we can also be creative, right? So this is in the design of losses, in the design of what do you do with the unsupervised techniques. And I think that will keep us busy for some time. At least that's my sense and hope. It would be a little bit sad if all of geometry was just replaced.
So just a short follow-up. So let's say instead of these data sets where, Google, Facebook, they have 300 million images.
Right.
What impact do you think would a data set of 300 million scans have on this type of research?
Mm-hmm. Well, if it's 300 million scans that are also highly annotated, right? At least I think the shape correspondence problem would be I mean, I don't think you'd need too much inductive bias in that case. I mean, probably even the simplest techniques would work. I mean, just having a basic feature extractor, and just, I don't think there's any need for kind of functional maps or anything like that. And I think in that case, it's unlikely. I mean, if they're unannotated, then okay, maybe you could still, you know, add some knowledge through modeling. I mean, one thing that I maybe just want to mention, I mean, this is like not a real answer to a question, but a small answer, is that like last year we had this paper on learning basis functions for functional maps. So instead of, you know, using the Laplacian basis, we use basically a learning pipeline to learn basis functions. And what was interesting is that there are basically two options there. So one option is you can either learn these basis functions, right, and then have like features and project your features onto the learned basis functions and then basically align those, or you can just learn the features directly and then align the features. And I mean, at least in our work, what we observed is that it's, you know, leaving this extra degree of freedom of like rotation and variance. So basically, instead of, you know, finding features that are directly alignable, having features that are only alignable, you know, once you project them, like on these learned bases, actually work better. And I mean, this suggests that there is something interesting going on. You know, it's not just trivial to find basically some features that you just directly match. You know, the fact that basically having this extra linear degree of freedom seems to help even outside of functional maps. So it's by no means a general answer, but there's something kind of a little mysterious there. And I think it also has to do with, you know, overfitting a little bit and like how difficult it is for the networks to learn certain things.
So maybe Peter, so actually I would say I strongly disagree with basically with where you try to push, and probably I hope that machine learning community has somehow overcome it. So I think when deep learning first worked in computer vision, right, it was very common to say, let's use this untamed power of GPUs, throw, I don't know, extra few millions of images, and make an even deeper and network with more parameters, and it will work, right? And you see it still maybe in some fields like NLP, but I think there came an understanding that if you know something about the problem better in some cases, right? And CNNs are a good example where you basically you want some form of translation invariance, right? So you don't want to depend on the position of the object in the image, and this argument was made by Fukushima in his neo-cognition in 1980, or maybe a couple of years before, that he was criticizing simpler perceptual networks exactly for this reason, for the lack of translation invariance. So basically get rid of the data augmentation with incorporating the right inductive bias in your architecture. And I guess geometry is a very good example where these inductive biases actually exist, and there are good models that are probably, they don't really describe the whole world, right? So we are not really isometric deformations, right? So we have, even the human body has more to it, but it's a good starting point. And basically what you cannot model, you learn then, but you need far less parameters and data and degree of freedom, and your architecture is much more lightweight. And I think the important question here really is, if you use this kind of inductive biases, basically how far can you go beyond this idealistic assumption, right, of, for example, isometry invariance. So the same thing actually happens in computer vision, where CNNs, for example, are not only translation equivariant, but they are also approximately translation equivariant. So this was shown by Joan Bruna and Stéphane Mallat, where they showed that if you deform a little bit your image by something, by some smooth field, that in the limit case you get, of course, translation, right? So this is absolutely smooth field, which is constant vector field, then you get exact translation equivariance. But if it's something that is sufficiently close to this translation group, that you still get something that is approximate, and you can bound this error. So we probably need more results of this kind for geometry as well, for the non-ideal transformations that can be where if you can measure some distance to this isometric group. So I think that's probably the direction to go.
I agree with
but still, so how confident are you that in 10 years from now, spectral methods will be a key part of geometry analysis?
Well, I don't know whether it will be spectral methods or it will be something else, but I think some geometrically meaningful or geometry-informed architectures will, in my opinion, will definitely be there.
Okay.
I think anything that can scale with increased computation, then it will stay there. It's here to stay. Right, so we want methods that, as we have more computational resources and as we have more data, they can keep up with the increased computation and the increased data. This is what we need.
And so my other question is somehow, yeah, my light is weird. Is that when I think about this non-rigid shape matching, I always feel that the prime application of that are humans. That's like the most interesting, and I would also think from industry market, this seems to me like really the dominant example of non-rigid matching. But if you scan a human, I don't really feel you naturally get this nice surface. And the first reason is the hair, the beard, the eyebrows, and also even something like, the nostrils or the mouth being open or closed. Like how do you correctly model the human when the mouth is open, or the ears? Maybe this, you don't want to have a huge interior model as well. Is there any way to really have I don't know, I'm really looking at this. Can there be a nice, somewhat standard reference model of 100 million, not 100 million, 1 million humans, let's say? And how would the human be represented? How do we represent the head in a nice way?
So there's a Caesar dataset, I think it was 10 years ago. It's 10,000 humans, I think. It's not public. I think you have to pay, but there does exist. And I think these are actual scans of 10,000 different people.
But how do I represent the hair and the beard?
It's just a single blob. You don't have. I guess what you're saying is you want really high accuracy representation for every part, like if you have a beard or something. These are,
I guess, would be nice.
So I think it depends on the application, really, because, well, first of all, what probably unites humans that, well, maybe with a few corner cases, with the exception of a few corner cases, we all look the same, right? We all have two eyes, a nose, a pair of ears, right, a mouth. So geometrically and topologically, we are very similar. So it is not outrageous to think that we can have a canonical model of a face that can be adapted. And this is actually what the industry does, right? So if you look at different avatars, I don't know, Snap, for example, right? So it's some canonical face that is adapted to the particular geometry of the specific user. Now, the eyebrows and the hair, so a lot of these can probably be absorbed into geometric texture. So you don't really need to model every hair of the eyebrows. You just need maybe some detailed bump map that will look like the eyebrows, but you don't really have the very detailed geometry of the hair. So it's probably a trade-off between what you need to model in details and what you can model roughly, but to make it look, or in some applications, to make it good enough, right?
There is also a problem of fairness, though, because we are assuming there is one notion, one meaning for what it means to be a normal human, right? Well, this is unfair because there are people with disabilities, so we have to be inclusive. No,
I totally understand it. Yeah, well, of course, I said probably normal means average or majority, right? So it's probably not a good term. But that's why I was saying in most cases probably you can model the face as a deformation of canonical face, and maybe there might be, I don't know, a person without an ear, then you need to treat it as a corner case, right? But I think this is not specific to this field, right? So there some exception.
Well, so I worked last year with a startup here in actually Monaco, and they work with athletes, and basically what they're trying to do is scan athletes and then track their like changes in their body type if you have an injury or if there's some development. So kind of for biometry applications. And they didn't use any templates. I mean, it was just like they had this kind of they call it dome, where you basically walk in and you scan. It's just like multi-view cameras, and it was not like super precise. I mean, you didn't see like individual hair scans, but it was okay. Basically, you get all the different body parts accurately, and for those applications, that was enough. And also, I tried some of our things. I mean, like our spectral methods for shape correspondence there, and it was working fairly well in those kinds of scans. I mean, basically, those were not people with some extreme disability. I mean, they're like athletes, so they're actually, much more like normal than me. But they like basically for tracking like changes in their body type, that was enough. But one thing that was interesting is, even for a single person, if you scan them at multiple times, you have certain things happening, right? Like you have the change of pose, or maybe you gain some weight, or maybe, like you had an injury, and actually reliably detecting exactly what happened, like the differences, that was actually the harder part. Because, we tend to kind of remove those differences. We say, okay, no, like let's make like the correspondence, let's make the alignment as good as possible, right? But kind of making sure, no, there's really actually something different here. And that was something that was not easy to do.
We would need something like a shape difference operator.
Yes.
So is what is the kind of basically what variations you need to factor out that are attributed, for example, to pose or to different muscle tonus, and which ones will be really due to injury or some weight gain. I think it's not a trivial problem. So this is here maybe I would agree with Peter that seeing a lot of data and knowing having some annotated ground truths saying that this is nuisance and this is real difference would be important.
Yeah.
So can I ask another question? It's because it's not only you, Max. We have some other people that love spectral methods. Or from my simple point of view, it seems that the medical image community, they have a lot of very similar problems. They do non-rigid shape matching. They do a lot of differential geometry, PDEs, at least traditionally, also before the advent of deep learning. But I somehow always perceive these communities as being almost parallel and not having a lot of interaction. So do you see any particular reason for this, or why is that the case, or is that even a wrong perception?
I guess you guys also have different experience in this. So my sense is, first of all, the major difference is that they often work with volumetric data. That's the first starting point, right? It's also true that they extract surfaces from some volumetric data, so it's not 100% accurate, right? So you do have, you can extract from a CT scan, for example, a surface. But I think that's the first actual difference, right? The second difference is maybe like more historic, because they have this, deformation-based techniques. Things are very local typically, so there's less demand for global correspondence, right? Like you typically want to deform things that are almost already there, right? But so this is maybe another slight difference. But I think it's also kind of cultural. So there's some, tools that they use, like there's this Deformetrica, I think, is a commonly used tool in the domain. It's like Alain Trouvé and his collaborators. So, and actually, I think, so we have like an ongoing collaboration with someone in medical imaging. And one of the hopes actually would be eventually to compare like spectral methods, for example, to some of the things that they use also. But the first major thing is to like bring everything into a common representation that, you can in a fair way compare things. One thing that I know is somehow amazingly to me in medical imaging, they don't mind like waiting, for example, a day to get a result. Like you press button and just roll, come back. And if it doesn't work, they just try again. Like they have an amazing amount of patience that I don't fully, like I wouldn't have it, So for them, like, okay, we have this method, you know, it takes a day, it's fine. So yeah, no, but definitely I think there's something.
So I tend to agree with Max. I think this is, well, probably depends on the initial condition, right? And this is also exactly my experience. So in medical imaging, well, as Max said, first that they typically the initial data format is volumetric, basically raster, 3D voxels. Second, they also, in many cases, let's say you have some organ that you capture, they have preferred way of capturing it. So they're usually also pretty roughly aligned. So that's why it's not outrageous to think that you can deform a little bit locally, I don't know, one heart into another, and they will roughly match. And this starting point of how you acquire data and how you think of data probably has led to an entire school of thought, right? In France, well, Alain Trouvé is probably one of the really representatives of this mindset. And they probably don't need these kind of degrees of freedom that you get maybe in more general computer graphics and geometry processing applications, where we say we have completely uncontrolled viewpoints and completely crazy deformations, right? Which I think it's really the case of how much basically what is your inductive bias, right? In a sense, if we were to use the machine learning term, maybe you don't need all these degrees of freedom that we often assume in computer graphics. And I think the reality is that this is probably the case.
Mm-hmm. But I know that, I mean, even Emma, I think maybe you worked a little bit now with some people in medical imaging. I know that Simone has worked. I mean, there are some people doing scans of.
Yes, I worked in cancer detection, but from 2D images. No, not geometry. But Simone, yes, Simone has something with brain in 3D. Yes.
Even nose. I know that they were trying to analyze the shape of the nose and how that affects.
Oh yeah. Mm-hmm.
I don't want to interrupt the discussion, but we've been at this whole thing now for 2 hours. So, which is not meant as to say that we can't continue. But I wanted to give everyone an option to say, I have other things to do.
Well, thank you guys. I really appreciate this. I mean, the discussion was really interesting.
Yeah, also from our side, thank you very much for the very lively discussion and for the great talk. Yeah, and